So, hello and welcome. Here we are in lecture 6, and today we'll be talking about encapsulation. And this is us kind of rounding out the collection of stuff where after today, that is after 2 weeks of lectures in this course, you should be able to do most things you can do in Verilog in Chisel. Now, maybe a handful of things you won't be able to do in Chisel you can do in Verilog, but there's also a handful of things you've already learned how to do in Chisel you can't do in Verilog. And then from here going forwards, you'll continue to learn just more and more parameterization, more and more ways to build generators and more flexible hardware. So let's go on to that. So like I said, today we're talking in particular about encapsulating things. So far we're kind of building very simple modules, but as we start to want to get bigger, we're gonna need to build bigger things, and simply having a single module do everything is gonna become eventually untenable, right? So we want to have ways to kind of collapse our hardware into kind of nice bite-sized pieces. So that way we can kind of reuse things and move them between different parts and have kind of sane scopes to deal with. Additionally, encapsulation is also a way for us to hide complexity, right? Where, ideally we'll build a generator someday that users can read the API rather than the code and understand how it works, and they only need to understand the interfaces and the parameters, and all details how it works underneath the hood is something we're going to try, encapsulate and hide inside of our implementation. In particular, we're doing a few things to incorporate this kind of stuff today. We'll be talking about how to use Scala features, things like we've been kind of dancing around but now take head on, such as, declaring functions, and, actually doing objects and using objects as well. On the Chisel side, we're talking a little bit about some things such as bundles, where we can kind of put these all together. Okay, make sure I didn't miss anything. Great. So let's go ahead and load in as per usual, and let's go from there. So you may have already kind of been able to intuit the function syntax in Scala for setting up a method. In particular, what you do is you will typically, like you see on the right here, you'll usually use def, function name, and then parentheses, and then the argument list. And so these are really trivial functions, so we just set equals, and we don't even need to have any braces, but if it's multiple lines, you are going to need braces. And now, one interesting thing to recognize about functions in Scala is that they return the last line, right? So maybe here it's very clear what's going on, but if we make this multi-line using the braces, that's what's going on, right? So you can see that in this case, given a number, this +1 function, of course, going to simply add 1 to it, and what's returning is the result of adding those, right? So I could have arbitrary computations above this, and then the last line is what it returns. And remember, this is kind of like we saw with the if statements earlier, right? Where the if statements, they're not just a control structure, but it's also something that returns something, right? So here's a function that does the same thing, right? Now, normally, if you follow in regular Scala, you have to kind of put your functions inside of either a class or an object. However, with this, nice rule to create inside Jupyter, we're able to kind of, in particular using Almond, the scripting language, we're able to kind of break that rule. But normally, if you want to define a function in Scala, it needs to be inside of a class or object scope. Some other little details. These arguments, much like the class parameters we saw before, they need to be, they're treated by default as val. So if you want to make them a var, you need to declare it a var. So for example, if I tried to, say n equals, n plus 1, it's going to yell at me. If I said I want to make that a var, it's going to be okay with that. Oops. Sometimes it's okay with that. But it's not going to be okay, right? So you have to, well, there's a reassignment to val. Yes, don't do that. That's kind of a short answer. If I seem puzzled about using var, it's because I managed to get through writing Scala for almost 11 years now and use var less than 0.5% of the time, if even. And so that's part of what's going on. Okay, so we talked about that. One more thing you see down here is you can also have a default value, right? So for trailing arguments, you can assign a default value, and that way I can say, give it 2 arguments or 1. So it's kind of a lightweight way to do overloading. Right? Of course I can, make this behave a little differently, but that's not too crazy, right? So this is, perhaps not a super crazy syntax, and it's kind of nice. I think this is really kind of a pretty simple little syntax. I like this a lot compared to other languages I've dealt with. It's pretty smooth. Okay, so let's keep going. So naturally, once we have functions, we want to perhaps call them recursively, right? And so, of course, you're familiar with recursion from some other languages you've learned taken prior to this course. The only interesting wrinkle about recursion in Scala is now you're required to specify the return type. So remember before when you declared vals, like in the prior slide, we just kind of, for the most part, did it. We did the kind of the label of types on our arguments, but otherwise, we don't really label types very often, and things kind of work out. When it comes to recursion, we're required to give a return type. So, so this is like a function, and using the syntax, there's colon, and then a return type. And then here we have a multi-line function, so we're using the braces. And yeah, okay, so, like usual in doing recursion, you should probably think about your base case and make sure it doesn't keep going on forever. And remember, this is the last line is what we return, right? So here we're using this if, and we're either returning a 0 or this else, right? So this is simply just summing up the numbers from 0 to n. That's what this little thing does. And you can see, of course, it gets 10, right? Because, from 0 plus 1 plus 2 plus 3, that's, 1, 3, 6, and then plus 4 is 10. Yeah, that works out. And, not only is recursion nice, kind of a way to kind of replace iteration-like things, but sometimes it's kind of an easy way to think about a problem. So, for example, here's a classic, recursive implementation for Fibonacci. And yes, that works kind of as we expect. So let's kind of go through this, right? We're going to call, maybe I'll first just call it on a single thing, right? So what's it doing, right? So it's going to call fib on 5, right? And fib comes in, okay, it's greater than 2. So it's going to fail this if statement and then recurse, right? So as you probably studied in prior courses, doing Fibonacci in this way, although it gets you the correct answer, it's perhaps not as efficient as we would like. However, there's a few things to point out, right? Number one, correctness does trump efficiency. So if somehow decomposing your problem to something that's, recursion-based that perhaps isn't optimal, but it's easy to reason about, that's still probably a win. Number two, it's for a lot of things we're doing in hardware, the number of iterative function calls may not be that high. So sometimes we can get away with, what might seem like a less efficient iteration space, only because, the number of iterations is small. But it's good to have efficient code when you can, of course. But anyway, so we kind of, have shown a brief demo. One thing you may have seen before, we'll kind of say again, if you ever need to have an empty return type, but you're required to have one, unit is the word you're looking for, right? And we've seen unit before, right? If I am trying to, find out what do I get, for example, if I say like val x equals, print line of hello, this should also be unit, right? So it's going to print that out, but then I should say what is x, and x is going to be unit. Is that not cut off? Oops, that might be cut off. But the type of, actually, I'm sorry, yeah, void, right? It's a unit. Okay, so there we go. Cool. Okay, so now we can do recursive functions or methods in Scala. You may hear me use the word function instead of method. I believe in Scala for most cases the proper term actually is method, but old habits die hard. Okay, so let's keep going. So you of course saying the same story over and over again, right? Is that chisel components are just Scala objects, so we can go ahead and build them however we can for a program. And so, like I said, the goal of this whole process, we want to try and hide that complexity, we want to encapsulate it. And what's nice about having kind of nice modular components is that, of course, we can declare something once and use it in many places. And also we'll see how ways to do things like using recursion to kind of not only perform iteration, but to kind of break our big problem down to much more smaller and more manageable problems, right? It's kind of divide and conquer style. And although what we've seen so far, we're kind of constantly putting things into a module, that's more of a byproduct of what we need to do in order to complete, testing and such. We have to kind of put things in a module. There's no reason why you can't make functions that just return snippets of chisel, returns a uint, returns a reg or something. That's totally fine. And put those together, right? So you kind of in mind almost start imagining the Scala code, which is, calling functions or doing whatever it's doing, that kind of, is going to go away, and you kind of think of what's the resulting operations called on chisel components to kind of start seeing what your hardware is going to do. And then we have seen things like module and bundle, and those are, classes defined by chisel that we often extend, and those kind of bring additional things into the scope, so to speak, and handle additional stuff, but chisel components can often exist outside of those. It's just certain things towards the end we kind of need those to have them around. Okay, so for remember from a couple lectures ago, we talked about, actually last lecture, sorry, what I call this delay end block. Really, people might call this a shift register, right? We have all these registers kind of in a row. So here's the prior implementation, right, where we had an input, some number of cycles we wanted to delay, and that's how many registers we're going to make. And so, well, what are we doing? We showed a few different implementations in the last lecture, but we said this one, perhaps with a var and for loop, kind of seemed kind of nice. And one of the things we liked about this one was not only could it do it correctly for, n greater than 0, but so you can see here, of course, there's two regs being defined, and he's kind of, connecting them over like this. We could also make this, for example, 0, and it gracefully, turns into a pass-through component with no registers blocking the middle. So that was kind of cool. So we can go ahead and replace our for loop of var with recursive function, right? So here we define a little helper function. And what does it take? Well, it takes how many more times the call itself and the last connection. And you can see the internals look a lot similar, right? Where we have our base case where if we ever get down to n equals 0, we just pass our input to our output. Otherwise, we're going to go ahead and put a register onto that that input, right? And then we kind of we're reducing our iteration count, and we connect this through. And so this is going to produce analogous hardware. I mean, it's a little hard with all the extra junk, but it's basically the same. And of course, once again, if we also want to simplify it, that works as well. So here's an example of why am I so bad with using var. Don't need to, right? This recursive function does it just fine. Now, if you were to, use a stopwatch in practice, if you really want to, do a lot of iterations, calling a function recursively is probably not the most efficient thing in the world, even with tail recursion. There's a way in Scala to actually even annotate tail recursion. In spite of that, like I said, those kind of performance details, for the most part, for the kind of things we're doing, these hard design things, don't come up, right? It's more important to get it right, get it clear, get it correct. And we'll worry about, oh my gosh, what's the fastest thing possible. So, I encourage you and invite you to try to kind of embrace this through kind of, recursive mindset to get things kind of nice and correct. One expression that's often uttered, which I don't always, not that I disagree with, I don't always believe it's possible or easy, is something called correct by construction. So this is kind of that mentality of, well, I'll break it down to really simple things, and if they're all correct, and I can put them all together correct, and it's correct by construction. But sometimes easier said than done. But here's an example of that. So maybe I've been talking a lot so far, so I'll pause for a second if there's any questions so far, as we've kind of gone through this brief crash course into using functions in Scala, and then recursive functions, and then using recursive functions to build up our chisel components. Mm-hmm. Yeah, so I'm just going to repeat this for recording. So there's a question about, talk a little bit more about Verilog. So yeah, so Verilog, remember, it's kind of annoying where you have this keyword reg, which doesn't actually guarantee the creation of register. It's more if you use a reg in just the right way, the CAD tools will infer a register. So in particular, the canonical way is you declare a reg, and then you put it inside an always block, and then you use a non-blocking assignment. Those are kind of the key ingredients to get a register inferred by Verilog tools. You can use reg for things that are purely combinational and will turn into purely combinational logic. So that's why it's kind of annoying where that name reg, it's so close to register, but it's not guaranteed to be register. That's one of those wrinkles of Verilog. So the question was, okay, wait a second, let's talk about this helper function's return type. So it's bool. If I don't make it bool, it's not going to be able to, exist as a recursive functions and needs that return type. So how does this kind of integrate in here? Well, its input is a bool, right? And so you can kind of see how that kind of originated, right? So our bool is what we're using the type for here. This could have been just as well, could have been a uint or something. So what do we do? Well, we initially called it, we passed in the first input, right? And then when you call reg next, or I should make it more clear over here, right? The output of reg next is a is a bool, right? It's the output of that register, right? So perhaps maybe make this more clear. I can go ahead and annotate this one over here, and that's not going to cause any errors because I'm correctly annotating the type. So last con here is a bool. Basically, I'm pointing to something that said chisel bool. So yeah, our input's a bool, great. And then as I continue to go through the output of these each registers, because the register is declared as type bool, and how do we know the register is declared type bool? Well, it's inferred from the input, right? So the input was a type bool, so it's okay if your input's a type bool, then your output's gonna be type bool for a register. So that's kind of what's happening. So there's a little bit of inference going on both by Chisel and by Scala, so maybe it's good to kind of make them more verbose. It's good to ask this question. So we had a bool input to the register, so the register, inferred a bool output type. That's what's returned by this regNext helper function. We'll actually learn about these kind of functions later today. These are actually, people might call these factory methods. Because you realize we instantiated the register, we didn't call the word new. And so we'll come to that in just a moment. So the return of this factory method is a bool pointing to the output of the register. And so that's what we put here, and then we can pass it on to the next one. And so on the right, that's kind of what's happening is we're doing the same thing, right? We're getting the output, which is a bool, and we're passing it on through the recursion to the next call to regNext, which is going to use that as input, right? So we're still kind of having the same effective pattern. We're just doing it with recursion rather than a for loop. I can understand at times, perhaps, a lot of us are perhaps more familiar with for loops, and it seems like a more natural way to write things. Number one, get it right. So this is the way that makes sense to you. Get it right. But I encourage you to try it out. Like I said, sometimes there'll be some situations where it won't be such a linear, simple iteration space, in which case having this recursion is kind of a nicer way to kind of decompose the problem. I encourage, and so this is just kind of a trivial example to kind of fit, compactly in one of these slides. But great questions. I'm going to pause for any more. Cool. Okay. We're going to keep going. Yeah. So now we're, already, we're using Scala functions to build up Chisel components, right? And they're recursive, right? So we're already, that was 0 to 60 pretty quick today's lecture. Let's keep going. Get out of that cell, and then we advance it. Yeah. Okay. So you may have heard me use the terms classes and objects kind of indistinguishably, interchangeably, and in terms of Scala, they're a little bit more nuanced. So most of what we've seen so far is a class, right? So class is kind of like defining a type, and you can have instances of a class. And so the correct word is instances. I often, perhaps, you might remember me say the word object, but no, the correct word is instance of a class. In contrast, an object in Scala is something that's a singleton, meaning there's exactly one of them. So when your program starts, you don't even need to ask for it. If you declare something an object, it exists, right? It's a singleton object. By contrast, a class, you need to instantiate an instance, right? Say I need new class or whatever. And so why do we have this singleton object in Scala? A few reasons, right? Sometimes it's kind of helpful to have things that, aren't encapsulated in a class. And so in languages like C, for example, you just kind of have things floating around. You want to have constants floating out there. You want to have other things. No problem. In Scala, outside this notebook environment, you have to have everything inside of either a class or an object, right? So you want to have kind of shared things, put those in an object. Those shared things can be either constants or mutable things. You can have stateless functions. Maybe you want a function that's something you just call this function. It doesn't necessarily need to be associated to an instance of an object. Put that in an object. To an instance of a class, Put that stateless function into an object, right? Or something we're going to see right here, something called a factory method. Now, this is something I think was a learning curve for a lot of us, myself included, in learning about Scala, is saying, oh, I've learned object-oriented programming, great. And then this language assumes something called the factory pattern, which may not be a household name for all of us. And what that pattern is basically having a different object construct an instance of the class you want, right? And the reason why this is nice is that object can do some things to kind of do some housekeeping for you. So sometimes it's pretty trivial, like we have here. It's kind of like a little bit like function overloading or constructor overloading. But other times it's very non-trivial. And it's nice to have this kind of separation of concerns of this is a class which has, certain data inside of it and perhaps methods operates on it. And there's something else which understands how to create that. So it's kind of this factory method pattern. Okay, so let's go see this example. So on the right here, we define a simple little class. It has, a couple arguments. And remember, these arguments are accessible internally. And so we define this, function inside of our method, sum, which of course adds them together. So we'll go ahead and comment these out, and let's go ahead and run this, right? So, we defined a class. We can instantiate it to use the new keyword. And we can call these methods on an instance of the class, right? I can't say, my pair dot sum, because that's not going to work, right? You need to actually instantiate it. Now, if I did this, you might think, oh, that might work. No, actually, I need to make an instance, right? So you need that new keyword to make an instance, and then on the instance, sure, you can go ahead and run the sum method on that instance. Now, this particular way of writing it, I didn't name an instance. I just made it. It's anonymous, and then I called the function on it, but I never really had a way to get back to it, right? This val is this reference. Let's just get back to that reference, that object. Sorry, that instance we built. And as we said before, in Scala, you don't have to put the parens on arguments as a style point. It's actually, you're encouraged to omit the parentheses if there are no arguments and the method does not mutate internal state. So if this is a, const kind of method, doesn't change anything, and there's no arguments, you're actually encouraged to not put the parens on it, because it makes it kind of seem more like a field, right? And even though in this case it's technically a method rather than a field inside that class, because you aren't changing anything by reading it, people seem to think that syntax is kind of simpler. So you may have seen, some of the collections, you may have seen like, oh, well, it's like, on my seek instance, I might have said, something like seek dot, is empty, right? Because that looks like one of these methods, right? Okay, and then here we have our companion object, right? So what makes the companion object? So you can have a class, you can have an object, they can have different names. If a class and the object have the same name, the object's referred to as a companion object. And depending on the way you use it, the language understands which one you're referring to. So, for example, we define an object which, this is, one singleton object, is one for, all time, has this var, which when the program first starts, it can be initialized to 0. And then, so of course I can go ahead and read that. And what's interesting is inside this object, we're going to use this factory method pattern. So we're going to call apply, for example. And then with that, we can, collect arguments. And then call, the constructor, or sorry, make an instance of class, and we're returning this, right? So what is this apply method doing? It's returning an instance of the class, right? So it's that factory method kind of at work, right? Apply is a special keyword in Scala. So when you call the object name with parens, without anything other, keywords, that's going to invoke the apply. So this is going to invoke the apply thing. So maybe the first time around, I'll go ahead and, give it 2 arguments. And so what does it do? Well, it's going to, make that my pair object. We can call sums. Also worth noting that, as a side effect, this is a liberal mutable thing we did here. Every time we create a pair, we're going to keep track of that. We're going to count how many these exist, right? So initially, when the program started, there were 0 of them. And then I made one. And so then I called that thing again. And now it says there's 1. Now you may be wondering, wait a second. Didn't we make a pair beforehand, right? What about this NPC one? We did, right? And we can see what happened here is, of course, we inadvertently sidestepped our accounting by instantiating the class directly rather than through this companion factory method, right? And so when you design your classes and your objects and interfaces, you should definitely be very clear how you expect users to interact with things. If you have a companion object, you usually kind of want people to kind of go through there rather than directly into the class, because you may be kind of controlling additional states or setting things up. Additionally, for example, it was easy for us to overload things, right? So in this case, we're able to say, hey, I want to have maybe a way to construct it with fewer arguments. And we went ahead and filled it in with a other thing, right? So that's also going to work. Of course, we get a sum of 3. But there you have it. So this is a lot to digest all at once, I'm sure. But the reason why I went through this is you're going to see this object kind of appear quite a bit in the remaining lectures in this course. And typically we're going to have an object where we're going to put things like, const would have for our project, kind of able to everything. Or maybe we're going to go ahead and define a stateless helper function chuck that into an object. Maybe you're going to want to define an enum, to hold certain state names or things you use for things. Easiest way to share around those kind of consts and enums is through an object, actually. And that sort of stuff, right? And so that's going to kind of help out with that. Great. Okay, I'm trying to think if there's anything else I want to mention about objects. Maybe I'll pause again for questions. It's definitely a pretty dense slide. So apply is called when you use the object name followed by parens with no method name. So apply is a keyword. So it's kind of a question of we're trying to describe, what happens when you call, my pair with just parens, and that's going to invoke apply. So that's a great question, right? So my pair with parens calls apply on the object. This also is my pair with parens, but it's new my pair, so it calls the class. Now there's one little feature we're not using here, but if you look it up, you can check it out. There's actually also a keyword dis for within the class, and if you use that as a function you overload, you actually can make an overload constructor directly within the class. Although that's possible, I recommend stylistically to do any constructor overloading in the companion object, and that way it's kind of more clear, it's kind of see what's going on. That way you have your class instances, which is very clear. Here's the data I need to do what I need to do, and here's how I operate on it, and then make the companion object worry about how to best kind of put things together and construct it. It's kind of a good style point. It kind of separates the two things. Sometimes people get so involved, that's how it goes together. And so I have a great reminder from the TA. I'm appreciative of this. So apply can be used a lot of places other than just companion objects, right? So apply just means, like I said, this is Scala's way of saying I want to overload whatever thing I'm inside of and then parens, right? So for example, if I was making a collection like an array and I want to have someone indexing into me, you can imagine they've overridden the apply function such that way they return. I don't think you can say array.get something, or you can just say array parens and index and it works. And the way it's doing that is with the supply function. So you can override a supply function. Right now it's really easy to do. Depending on how you set your class hierarchy, which we'll cover more later, you can use certain keywords to make things harder or easier to extend and that sort of stuff. To be honest, I'm not sure I can answer that correctly. So, what I would say, sorry, to clarify the question is apply inherited from some sort of, parent object somewhere? It definitely gets passed on when you inherit things. In the case of this particular object, which I didn't give any inheritance to, where does that apply come from? Is there one I'm overriding, or is this from scratch? I believe it's from scratch. As I mentioned, depending on the nature of your class, is that, right now these are just classes. If you have like an abstract class, or if you have other things like that, and there's a bunch of keywords in Java that kind of have similar but different meanings in Scala. I'm not going to go super far in that kind of stuff for now. We'll come back to that in a few weeks. But for now, you can build a class with some instances, no problem. And if you want to have this companion object, like I said, it's good to kind of put shared things into, as well as to declare these factory methods to kind of declare things. Oh, so yes. So the question is basically saying, wait a second, why do I have, two applies? Would this work fine with just one? Yes, it would, right? So this will work just fine with one apply, right? The second apply is me deciding to overload this function, right? So I said, hey, what if somebody wants to declare something with only one argument, right? Now, pragmatically, right, we know we can do this, right? And we'll have the same behavior, right? However, even though you could use a default value, I didn't, just to kind of show the benefit of having another constructor. And what's kind of about this particular pattern of setting things up is that this constructor calls another constructor, right? So we have, even though there's different ways of getting into the object, because we're kind of following the same code path and there's less code duplication, hopefully less chance for an error, right? It's kind of the goal. And now you have me curious, what happens if I leave this in here? Is it going to yell at me? Nope. But I'm really curious which one is running. I'm not sure, to be honest, but there's some sort of resolution rules for that. That's probably, if you have ambiguity about which one is calling, it's probably a sign to rethink your type signatures. Yeah, there's also another endorsement from the chat from one of the students saying companion objects are pretty special. Scala uses them for a lot of things. Yeah, they're pretty special is a good answer. So yeah, so we've been using them, not realizing it, right? So now we've seen this slide, we understand that every time we're getting some sort of what we think is an instance of something, and we're not using the keyword new, we're probably calling something on a companion object, right? So all those things we saw in reg before, like reg next, reg init, those are all companion objects for a reg. We didn't say new reg, right? So that's kind of what's going on. Cool. Let's keep going. Oops. Should be able to advance. There we go. All right, so kind of taking what we just learned and putting some practice for Chisel, right? So we had this counter in our first lecture this week on using state. It's the same code, just copied again. And this counter is unmodified, but we just wrapped it in the companion object, right? So what's the consequence? The consequence is before we, say, hey, I want a new counter. Okay. Now that I define a companion object, I can, remove the new, right? Removing a new isn't the only reason why you build a companion object, but for the simple example of just taking full advantage of the object, it will work. Cool. So that's just an example of this working. As I said, this is a second ago, right? Things like mux and these other things, those are actually being called on objects, right? And they may under the hoods be using instances of classes, but that's kind of what we're seeing. Okay, so we can take one step further, right? So we've been encapsulating things. We've been talking about, so nice to kind of have things encapsulated and contained. But as I said before, a chisel module just kind of brings certain things in a scope. You don't necessarily need a module, right? So in particular, what happens if I just make a counter, but I don't extend module? So notice there's no IO, right? So what am I doing here? Well, I'm taking in a parameter. We're going to use that for our maximum value. We're taking in a bool. Remember, bool is that chisel type. So we're taking in an enable signal. And, we go ahead and declare our register for our count like before. We still do our when statement just like before. So it's perfectly valid chisel. And as we have, if it's enabled, we're going to go ahead and increment potentially. If we're less than max, we add 1. If we're at the max, we reset that 0. And so after all this, we've created an instance of this thing, right? Now, here I have my companion object, my counter. Same name, so it's a companion object. We have our apply function. So take in those two arguments. And what do we do with those? We use those to not only make an instance of my counter. If we gave someone an instance of my counter, that actually might not be as helpful as they might think, because they have this Scala instance, but what they really care about is kind of what's inside of it, right? And so in particular, what they want perhaps is the output. So we go ahead and the last line of our apply method is what we're actually returning, and we're returning this field of this instance, and that's what's going to be the count, right? So this should all compile out, great. And if you go ahead and look at instantiating this, in order for the sake of writing Verilog, we need to put it inside a module, because otherwise, what's it inside of? We can go ahead and instantiate that, and yeah, we can have our enable and our count. So we make an instance of this, and then we attach it to count. And there we have it. It's the same counter from before. I can probably even cut out this line just fine. Yeah. So great. And so let's kind of pause and show what we've done here for a moment, right? So we've used Scala's class mechanisms to compartmentalize and encapsulate some amount of chisel functionality, but it's not necessarily in a module, right? We put in a module and instantiate over on the right side, but on the left side, at this point, when someone calls, my countering it, when it gets what they return from it, they're only getting, just this collection of chisel things, right? And this actually is very helpful at times, where when it comes to composing things together, modules are a little bit rigid, right? Because modules need you to have things with an I/O. You need to connect both sides of the I/Os. I/Os are kind of like wires, right? You connect one side and the other side. And modules also appear as modules in the Verilog. Now, when you declare things like this, where you kind of have this kind of floating, thing, it's basically effectively inlined wherever it's instantiated. And sometimes that leads to, more concise implementations downstream in the tool flows. In terms of actual hardware, whether I put everything in a module all the time versus sometimes having these, modulous classes, it should be the same, right? Any decent CAD tool should be able to recognize, oh wait, these are just wires connected through to each other. It can understand what's happening. It can figure out what's connected to what. It'll be fine. But in terms of us kind of reasoning about things and making sense of things, we kind of use modules a little bit more deliberately about kind of thinking this is something we kind of want to have as a clear boundary, have clear IOs on. But there may be things inside of that module that we may want to be more clever with and more flashy with. And one thing we'll see more next week is for these classes that are modulous, that aren't actually modules, part of the advantage of doing them isn't just the fact you can inline them. We can actually also define methods on these classes that make them more feel kind of like a programming object, less like a module, right? So that sounds confusing. Maybe more clear to cover that next week. But for now, that's kind of the point, is we're able to kind of start playing around with stuff. So like I said, the chisel objects are kind of building in our programs. These are really kind of more of like a side effect for programmers. Right in the Scala program, which does what it does. And along the way, it's constructing this graph of chisel components, which gets turned into a circuit by the tool flow. And so here's yet another example of that, where here we're kind of, swimming in the deep end, so to speak, where we are making chisel components without putting them in a module and, able to return and do just fine. And then, yes, it tosses the module to print it out, but you can do that for a while. Cool. Okay, I think we can continue if there's no more questions. So we just did all these examples of a counter. And what's the punchline? The punchline is, don't worry, chisel has one built in. So it's technically inside chisel3.util. I just wanted to, use examples of the counter as a very simple component to understand. And so their counter actually follows the structure I just described, right? Where when you use their counter, you don't say new counter, right? You just say counter. It takes an enable and number to count up to. Now what's interesting is they actually return not one thing, not the count, not just the count, but two things. And so this is the tuple syntax in Scala, where you can have tuples and you can return a tuple, you can assign a tuple like this. You may see this in Python. And so what's interesting is it returns not only the current count, but also a bool if it has, reached the target value. So, here's their implementation of it. We can go ahead and get the Verilog, and perhaps it won't look too different from what we were expecting before. We can see, okay, well, it's going to wrap when we're going to keep adding 1 to it. We're going to wrap when it reaches that max value is 3, because we wanted to build a counter that counts 4 things, right? So you count 4 things to go from 0 to 3. And you can see inside there, right? Of course, on reset, it goes to 0. And then if it's enables, you take this wrap value T1, wrap value T1 is this. And they actually don't even bother worrying about the mucks like we did. They kind of take advantage of the actual wraparound. But I think if this was not able to wrap around, it's probably going to be more smart. And then we can see it actually recognizing the need to reset itself automatically. So you can see, once again, this is kind of nicely designed internals inside this util library, where our version, always kind of did that wrap check, versus theirs recognized, oh wait, just by natural binary arithmetic, it's going to wrap around anyways. I don't need to do anything special, so it kind of took that out. This is an example of you kind of get more sophisticated for your generators. Now, another neat little nice thing they've added recently to the counter module, or counter generator, is you actually can use the Scala range syntax. So rather than just saying I want to count 5 things, you can say, here's a range. And so, for example, if I want to do 0 until 7, and at this point the argument doesn't really matter to the other thing, that's just fine, right? And you can see, for example, yeah, I said by 2, so it's actually counting by 2. And so yeah, so I give this kind of an example of here's a a built-in generator in the util library, and you kind of basically we've covered so far can already kind of understand the things that go into this, right? And so that's kind of pretty cool. And you can imagine counters, of course, are extremely helpful components in designs where you constantly want to have something doing something where it takes some number of cycles, and rather than having like a discrete state in a defined state machine, like a switch statement for every single possible option, you often use counters to kind of count passage of time to kind of reset your counters and stuff like that. And there's more flavors of counter linked on these pieces here. Cool. Maybe we'll go ahead and revert that. Alrighty, and then we keep going. If there's no questions, okay. So let's talk about bundle. So bundle is the way in Chisel we kind of put things together. It's a aggregate type that has named fields, much like a struct in other languages. We've learned about vex, which are another aggregate thing, but it's indexed numerically. And so far we've seen bundle just to make I/O interfaces, right? But that's actually not the only place they're going to be used. And what's kind of nice about this bundle is, rather than having to kind of write out all these fields every time you declare a module, you can kind of declare it once and use it in many places. And as you'll see later on, you also can declare a bundle, and then use that within another bundle to kind of construct things up hierarchically, right? So it's pretty cool. So for our first step, let's just imagine we're doing some sort of numbering system. So we're having a magnitude. It has a field x. Sure, it's a uint. Here's a custom bundle class, and so that's no problem. We go ahead and then instantiate it, and we can assign this, and so it's just gonna be a simple output. Not too fancy, but cool. What's nice now is I've defined this bundle type, and so I can use this mag anywhere else I want to talk to this thing. So now if we see in the coming slides, we can go ahead and start kind of augmenting that. So how can we augment it? We can augment it in a few different dimensions. So one dimension is with inheritance, right? We can extend it. So the mag type has only one field x for like the number. The sign and mag type, now we've added on a field for sign, right? So we're able to take the unsigned one and just add another field on for sign, for example. This is some boilerplate. I'm gonna come down in a couple slides, so just for now, cover your eyes. All right, so that's cool. So you can instantiate a bundle, you can extend it. We'll cover inheritance in more detail later on, but this is kind of just a day one inheritance. And then what else can you do with it? Well, you also can instantiate other bundles within a bundle, and you can even put them inside of a vec, right? No problem. So that's what we did here, right? So here we decided, okay, well, we defined a number, we add another field to it, so there's x and s inside this thing. We can maybe make a pair of them by putting two of those in the vec. And so what do we have? Okay, we go ahead and instantiate our new bundle, and if we look at the fields, right, you can see, okay, well, pair sign mag has a field called nums. Nums is a vec, and we index in the vecs with the round parens. Okay, and so we said it has 2, so 0 and 1 are both valid. And then each of those are sign mag, which it has an s and x field. So okay, those are the 4 fields, and of course we can run this code in a second to get the Verilog. A few things to note here, right? So obviously it's kind of cool to have this extension and nesting and composition, that kind of stuff. But oops, we just lost one of the cameras. Let me try and fix that real quick. See if this fixes it. Yes, it does. Okay, that was a great hacky fix. So you can see, okay, it's kind of fun to nest things or to extend things. But in terms of readability here, let's pause for a moment, right? If I'm only looking at the code at the point of, here, and I'm trying to find where all these fields come from, the fact these fields came from 3 different code blocks perhaps not the best for readability. So my own personal advice on this is, obviously there's great times when you can reuse things. And so when you can reuse things, that's a good time to kind of separate things out and factor things out differently. If something is not reused, and it's only used once, it's better kind of, inline immersion, so to speak, so that way it's kind of clear to read only one place. And so, of course, for today's lecture, it's only used in one place, but because these slides aren't very big, but you can imagine perhaps there's a way you want to have these things separated out, or maybe there's places you want to use only mag and not use sign mag. Right? But yeah, this should work. If we take a look at this code, oops, I got to make the scrolling on. But yeah, you can see there's our fields. This is the way Chisel happened to decide to collapse the names. But cool. Okay, I'm gonna pause here if there's any questions so far. Okay. So with that in mind, let's keep going. So yeah, let's talk about that clone type thing I just mentioned. I would argue, in my personal opinion, this is probably the ugliest required boilerplate. And it's one of these things where there's no good reason for it other than the Chisel language developers are kind of backed into a corner. And for now, this boilerplate is needed, and it's been needed for quite a few years. They're working on trying to remove it. They have some pretty cool workarounds to make it smoother. But for now, it's kind of needed. So basically, what is it? Well, when you make your own bundle, and either you parameterize it or extend something, you're probably going to need this, right? And so what is this thing you need? Just copy and paste this code. Make sure to replace this with your class, of course, and if there's parameters, put the parameters in there. And, so what's going on kind of under the hood? Well, under the hood, there is this clone type method, which is normally available in Scala classes. And the way bundle does things, which we extend as well, it kind of inadvertently breaks that. And kind of need help it move along. Like I said, future versions of Chisel hopefully will have this removed. But for now, it's just one line in a bundle. And often bundles are much bigger, so it's not so bad. Yeah, it's kind of annoying. So, for example, here we ran it just fine. It's assigned magnitude. In this case, I classed them all into one bundle definition. This is the code we expect down here. Oops, I don't know if I can scroll right now. Oops. But if, for example, were to remove this clone type, it's probably going to growl at me. Yeah, there it growls at me. So this code would otherwise be completely valid, right? You're like, what the heck did I do wrong, right? This looks like totally valid code. If it's involving a bundle, consider adding this clone type method. Like I said, so for really simple bundles that don't extend other custom types and don't have any parameters, like I had in the prior slide, which is kind of carefully constructed, it was totally fine. Notice I had a preset width here. However, if you start having parameters and subclassing other types, extending other types, you probably need this clone type. So yeah, it's annoying boilerplate, but just copy it and get it right, and then forget about it. Cool. Let's keep going. So there's some more stuff you can do with bundles, and that is there's the flipped operation and the bolt connection operation. So first, we're showing the bolt connection. So here's that sign in mag. And the way I defined it, here I've defined that clone type, of course. Defined, okay, X is, a uint, S is a bool. And I actually didn't bother putting output or input on these. But at some point, you do need to have that. Maybe it's better if I go back a slide to show this particular nuance. Let me go back. Oops. So for example, if I didn't label this output, and I removed this output, it would be mad at me because it's like, oh wait, I don't know what direction that is. So I can put, output on this, and that's to make it happy. Or you can even put it at this level, right? So I can remove both of these outputs, and then say all of this is an output. Now, because we have these concise model definitions, we're trying to squeeze into slides. Everything's all going in the same direction. There's no requirement within a given bundle that all things go the same direction, right? It can be some in, some out. And that's what we're kind of getting to in this next slide, right? So here we didn't bother defining directions here, but when we instantiated them, we did. So we said that's an input, that's an output. Here's that unique, interesting operator. So this thing does is it's called a bolt connect. If you have the same bundles, it will connect all the wires up, right? In particular, in this case, it knows which side is the input and which side is the output, so it does the right thing. And it works, just fine. It's the pass through. I could have easily actually swapped these, and it should still work, right? Because it understands looking at these modules, which is which, right? So these bolt connects are really helpful as you start getting more complicated, more sophisticated designs, especially as you start having bundle types nested within bundle types. You can go ahead and connect them all up once, right? So you can imagine, here's my network link, right? This network link has, an address field, a payload field, a valid field, a wait field, whatever. Pull those fields into a bundle and you just bolt connect them all at once. Cool. So that's the bolt connect operation. Now I'm gonna quickly modify the code to show flipped. And so, for example, if I defined these to be output, this works because this says this is input. But instead, if I just had these as sign and magged, I want this to be flipped, right? And so as the name implies, it's going to do the right thing. If I didn't make this flipped, it's probably going to complain that it's output to output, right? So one of them needs to be an input. And so flipped is a way to get that behavior. Oops. And I can't spell it right now. Great. So this is a very common thing you're going to see where you maybe define some sort of bundle, which you kind of use as like a standard link in your maybe some sort of interface you're using. And yeah, you kind of put it in one place, and you're going to put it someplace else and then call, flipped on it in order to get the reverse direction. Now we can kind of mush them together with the bolt connect. We're getting there. Yeah, so today is kind of the day of all these different ways of how to collect and combine all of your stuff and kind of encapsulate in ways that's kind of more hierarchical and nicer to deal with. So as one last little wrinkle, there's this thing called option in Scala we're kind of going to use, right? And so you may have seen this kind of inadvertently. Now we can talk about this more formally. So what option is, it's a parameterized thing that can indicate that something may not exist, right? So in a lot of languages, as a programmer, we kind of assign like a sentinel value to kind of track something that's not there. So we say, for example, is this number -1 to know that it's actually not a real argument? Or, is this pointer null to notice there's actually not any data there? Scala says, let's not do that. Let's actually just have a separate way of tracking that. So you have this option type, which it's like a super type, and is either none or some. And it's something that actually exists, right? And so none, means that there's nothing there. And some means there's something there and here's the value, right? So if some exists, that means that should be a valid value you should be able to do things with. And there's a lot of ways to deal with these options. Some of the methods you deal with in Scala will return an option. A very basic way to interact with these is to directly call these methods on it. So if you have something is an option, you can call .isDefine to return true or false if it exists or is none. And if you know it exists, you can call .get and get the actual value out of that sum. Right? Otherwise, you're going to get an exception, right? So here's a little example. So we defined an option of type int, and we said it was sum of 4, right? If I try to say, O plus 2, this is probably going to be a little grumpy because it's trying to add 2 onto sum is maybe a bit of the other way around, right? It's unable to figure out a way to add an integer plus an option, right? Now, here, because it's defined, we get the value, right? If I didn't define this thing, of course, it's going to get none. And, if I, for example, didn't bother to check if it's defined and just tried to, access it, and it was something, it's going to work, but that's risky because, of course, if it was nothing, it blows up, right? But the reason why this is helpful is there's going to be times where for parameterization, we're going to want to pass around, oops, I didn't mean to go that high. We're going to want to pass around options. And with options, we're going to be able to kind of capture just something existing or not existing. So as you can see right here, we're going to make optional fields in the bundle using an option. So let's go ahead and see that on the next slide. Call calling this bundle type maybe pair, right? So we have a bit width, sure, and then there's this Boolean has y, right? So normally we always get x, but question is, what about has y? So if has y is true, we get some thing here, right? We wrapped it in some. If this is false, we get none. And then, yeah, because we had enough funky stuff in this bundle, we had to put a clone type in there. Okay, like I said, boilerplate, ignore that. So then what happens inside our module, right? So our module, we're taking this Boolean, if we're going to use a y, so when we instantiate we pass that on. And then if we're using a y, we're going to go ahead and attach that output. But if not, we're not, right? So if we go ahead and run this, what do we have, right? Well, because initially we said we're using the y, we're going to go ahead and define 8-bit wide fields, and we're going to set x and y both to 4. But what's cool is if we say, you know what, we don't want y, it's completely gone, right? It's not just pruned by dead code elimination, it never even made to the point to even be pruned, right? And so now already our bundle is a pretty cool thing, right? So in the beginning we had these bundles which were very static and anonymous and defined right in our modules in a very rigid kind of like a classic Verilog style interface. And already in the last week we've kind of seen how to use Vex to have an arbitrary number of inputs for some things that are indexed. And with today's stuff, we now can see how to have optional fields as well as nested fields using other bundles, or even extending existing bundles to kind of do things. So you can kind of see how very quickly these interfaces now kind of become much more parameterizable and constructible things rather than such rigid kind of locked in things. Cool. Okay. I think I only have one more slide. Yes. So when I introduced Seek earlier in the week, looking at the lab, I omitted to cover one method. So we saw the Seek, but this is something that exists in Locklish, not just Seeks. We saw use fill as a way to kind of populate collection. You can use fill to say, hey, I want n things of this. Tabulate's something a little bit more general, right? What it does is it says, hey, I want to create n things, and rather than just putting n identical copies of something in there like fill does, instead it says, you know what, I want to call a function to produce those elements, right? And so that function you're calling, we're actually going to have it be an anonymous function, which we're going to cover these in more detail later, but for now you can kind of see that right here where it takes in one argument, which is the index, and you do something with it, right? So it's the argument, and then this is the kind of syntax that it's going to be an anonymous function, and then the result, right? So we go ahead and run this out. What do we see? Well, of course, if I say, hey, I want to just fill a Seek with 4 zeros, we saw that before, no problem. Okay, I want to tabulate, so I want 4 elements, and go from 0 to 3. And what does my anonymous function do? It just takes I and then returns I. So in other words, the identities. Yeah, so we had the index of 0 to 3, and we got a list with 0 to 3. Now, as an alternative, like that, if that's all we really wanted, you could probably do this, right? This should work. Oops. Mind you put that in parentheses. Yeah. Okay. Yeah, so that does work. You'd actually probably be happier if I put it. So yeah, so if that's all you wanted, of course you could do simpler. But you can imagine you might have something non-trivial here. It's not just I. Or sometimes maybe it is I. But then this last one, using some interesting syntax, there's this wildcard replacement you can do with underscores. So if you know you have a anonymous function, and you're only going to use an argument once, it's going to go ahead and just bind automatically. So it's even more concise syntax. These wildcards are pretty cool. Sometimes they aren't going to work, and they're going to do crazy things and blow up in your face. And so you got to use them a little judiciously. But in this case, it's pretty helpful, right? So in this case, we said, hey, for indexes, multiply it by 2. So now we get 0, 2, 4, 6. So that's an example of tabulate. Like I said, this appears in, I think, the labs. And it's kind of a helpful way for things like, maybe you want to fill out a large collection before you toss into a ROM or to a memory or something. Cool. Okay. That's that. Any last questions? Sure. Okay. Mm-hmm. So yeah, the question is why did I have to use clone type here? Didn't I say it had to be used for parameterized bundles? For parameterized bundles, or in this case, it's not extending bundles, it's extending a subclass of bundle. That's the other wrinkle here. Um, my advice is if it's a really simple situation where you're extending bundle directly and you don't have any parameters, try it out without clone type. If it growls, just toss a clone type in there. And like I said, hopefully this is something that if you want to watch the most recent Chisel talks, this has been known for a long time. The reason why it's been far down the list of issues is because often bundles get pretty big and one line clone type boilerplate isn't so bad. But yeah, they're trying to get rid of that, make the language even more polished. No problem. Okay, so that's all we have prepared for today. I just want to kind of close out, remind where we are in this course. So yeah, we've done 2 weeks. By now, you should mostly feel pretty empowered to do whatever you could do in Verilog in Chisel for the most part, as well as we're already kind of starting to see some parameterization and kind of constructing these bundles as we would like. Assignment-wise, we've already posted Lab 2, which is due next Tuesday, and I should be ready to go on the internal Jupyter system as well as push to the public internet for those who want to try it out there too. And homework 2 hopefully posted probably late tonight, early tomorrow, and I'll be due, of course, next week on Thursday. And you'll have a chance to kind of put these things into practice. And with that, I wish you all a happy Friday and a good weekend.